and it's my pleasure to introduce to Álvaro Krüger, and today he's going to talk about finite topology surface of constant mean curvature in hyperbolic 3-manifolds. Thank you.
Thank you, Jose, for organizing this beautiful conference. Thank you all, the organizing committee, which I know it's not just Jose, but all the people in IMPA. Thank you for allowing me to speak today, and thank you all for coming here. So I'm going to talk about a joint work with Bill Mix. We are working in finite topology surfaces of constant mean curvature in hyperbolic 3-manifolds of finite volume, basically on finite volume. So the question we want to answer is, let N be a complete, non-compact, hyperbolic 3-manifold of finite volume, and by hyperbolic I mean constant sectional curvature equals -1. And we assume there is, we want to understand the immersions of non-compact surfaces of finite topology which has constant mean curvature in N. So there are a few questions which we would like to answer. For instance, when is this immersion proper? And if it is proper, how does it goes inside N? How is this immersion related with the geometry of the ambient space? And when phi can be an embedding? So just to say, the results I present here are inspired by works of Colin, Hauswirth, Mazet, and Rosenberg, which recently started studying minimal surfaces in hyperbolic 3-manifolds. So it's a natural next step to understand how does the constant mean curvature case works. So this is what I want to tell you today. So the first theorem we obtain kind of answers the first question: when can this immersion be proper? When is this immersion proper? We are calling this the properness theorem. So here is stated in this setting I just told you, but actually it's a little more general than this one. We allow the curvature of the ambient space to vary until -1. So it's a Hadamard manifold with negative curvature. And here what we find is, let sigma be a surface of finite topology, non-compact. That's important. I will most certainly forget the word non-compact all over the talk, so let me just tell you, everything here we are doing is non-compact, both the ambient space and the surfaces. And we assume that this immersion has bounded mean curvature, so it's not necessarily constant, just bounded by 1. Then, if for every end representative of an end of sigma, the length of the injectivity radius function is 0, what does it mean? It means that the surface closes in the ambient space. The injectivity radius at every end starts to close up. Then we find some nice results. First, it has finite total curvature. Actually, this is not a result of ours. This is just an intrinsic property of surfaces which was known for a long time, but it's interesting in this setting here. For each angular end, the induced map is injective, so the ends are immersed non-trivially in the ambient space. And moreover, if this condition holds, then the immersion is proper. You can't accumulate in a compact set. So I'm not giving the proof of this theorem today. If someone wants to talk about it, I'll be happy to discuss it. The focus of the talk today is the second theorem, which is the finite topology theorem, which Bill presented the statement in his talk Monday, which says, in the setting of a complete non-compact hyperbolic manifold of finite volume, and you fix any h less than 1, and you look at properly immersed surfaces with finite topology and bounded mean curvature by this constant h. So we find an area estimate in terms of the Euler characteristic of sigma, and we know that equality holds if and only if sigma is totally umbilic and of constant mean curvature. Moreover, it has finite total curvature by the last theorem, and if in the case of the constant mean curvature, every end representative of sigma is asymptotic to something. What is this something? It's what we are calling the standard ends, which are totally umbilic annuli, which are properly embedded in the ends of N. With finite multiplicity, thank you. So the case of minimal surfaces was proved by Colin, Hauswirth, and Rosenberg, as I told you before. So what is important about this theorem, we assume only immersed surfaces, so we don't assume embeddedness. But of these two first results here, we don't need the curvature to be constant, just bounded by a constant away from 1. And in the constant mean curvature case, we find a little more. So next result I intend to show you today is the existence theorem. So given any age less than 1, we can find an example of a constant mean curvature surface H of finite topology inside, properly embedded inside some non-compact hyperbolic 3-manifold of finite volume. So this is what this statement is saying. And moreover, this embedding can be chosen to be totally umbilic. So it will actually have the ends, exactly the ends which every other surface is asymptotic to. So this theorem probably have a little improvement we are working at. We also think that it's possible to do this with an arbitrary topology among the possible topologies. It follows directly from Gauss-Bonnet theorem that the plane and the cylinder cannot happen with constant mean curvature inside a hyperbolic 3-manifold. So other than these topologies, are the others possible to find? And we think that the answer is yes. Also, we have a non-existent theorem. When H is bigger or equal to 1, there is no possible to find a constant mean curvature surface with H mean curvature with finite topology properly embedded in a hyperbolic manifold of finite volume. This is not true if we just assume immersed. There are examples of properly immersed surfaces of constant mean curvature H bigger or equal to 1 in the ambient space. So let me give you a little history. There are some results, classical results by now, which imply properness of surfaces in some ambient spaces, especially in R3. So the theory of coding mini-cos says that embeddedness and finite topology in R3, then you are proper. Then a little afterwards, Mix and Rosenberg improved their result, showing that embedded and positive injectivity radius in R3 implies properness. And recently, Mix and Tinaglia extended these results to the constant mean curvature case. So if you have finite topology or positive injectivity radius and you are embedded in R3 with finite topology, then you are properly embedded. In some other ambient spaces, what is known by now, well, we know that this result doesn't hold in other ambient spaces. For instance, in H3, for any H less than 1, there are planes which are embedded, but not properly embedded and with constant mean curvature that particular H. That is a theorem by Koskinuser, Mix, and Tinaglia. And this result is actually sharp because if H is bigger or equal to 1, some similar result as it occurs in R3 happens. Any surface of finite topology which is embedded with constant mean curvature H should be proper. Also, a similar result holds in H2 cross R. It's possible to find H planes which are embedded in H2 cross R for any H less than half, which are not properly embedded. These are in 2 papers by Koskinuser, Mix, Tinaglia, and by Tinaglia and Magdalena Rodriguez. However, the similar result to this, it's not clear in H2 cross R. We don't know. It should be true that if H is bigger or equal to 1, a surface of finite topology embedded in H2 cross R with constant mean curvature H should be proper. This is related to a more general conjecture that has meaning with the critical mean curvature of the ambient space. If M is simply connected and you have an embedded surface of finite topology which has constant mean curvature bigger or equal to this critical mean curvature, then it should be proper. This is still open. Is R3 with homogeneous metric? Or or covered by it and with h bigger. Yeah. Okay. So before I prove the theorem, the properness theorem, the second one I presented you, I will talk a little about the hyperbolic manifolds of finite volume, give you some pictures, show you the geometry of these manifolds. So fix a hyperbolic manifold of finite volume. The picture you should keep in mind is something like this. It has a compact part, which is called the thick part, and with a finite number of ends here. I'm drawing a picture with 5 ends, which are called the cusp ends of the manifold. And these cusp ends here are very interesting and important for our proof here. So each one of these ends is foliated. Well, it can be modeled by a horoball in H3 divided by a group generated by 2 parabolic translations. So it's like, here I'm using the half-space model to H3. So the horizontal planes are horospheres, and all this region is a horoball. And every parallel plane you get 2 translations that leave it invariant, one in this direction and the other in the other direction here. So you quotient this horoball by these 2 translations, and you generate a lot of torus, many tori here that goes to this end and foliate this end. So each one of these ends is isometric to this quotient of a horoball by 2 parabolic translations. Let's try to begin to prove the properness theorem. So we consider a proper immersion of a surface of finite topology in N with bounded mean curvature by this constant h less than 1, and fix an annular end of sigma. Just to remember, finite topology means that you are a compact surface with a finite number of punctures, and each one of these punctures gives the topology. It's an end of sigma and has a topology of a half cylinder. So since this map is proper, then every one-ended representative, every little neighborhood, a sufficiently small neighborhood of these punctures, shall be immersed completely inside one of the ends of the ambient manifold. Sigma could come inside here, go back one end, could come inside and go back and come here, but eventually could do this many times, but eventually it will stay in a single end, otherwise it wouldn't be proper. So we assume that this end is immersed inside a cusp end of N, and just reparameterize this end by t bigger equal to 1, and we assume that the boundary lies into this region here, a compact region in between t equals 1 and t equals t naught. So this is the picture we have right now of one of the ends of the ambient manifold, of the surface in the ambient manifold. And we want to prove things about this. So the first claim is that this immersion here is non-trivial, topologically immersed non-trivially. To answer this is quite simple. If it was trivial, you could lift this isometrically to a cylindrically bounded surface in H3, which means it stays at a finite distance of a geodesic, and it will be properly immersed with compact boundary in a horosphere and mean curvature less than 1. And you could just take Delaunay surfaces, which will converge to a chain of spheres, and find a first contact point, which contradicts the maximum principle. So we know that this end does not lift to H3. Now we begin something. The first claim, actually, the actual first claim here is to show that for almost every t, the intersection of the end with this tori here is transverse, and there is a unique homotopically non-trivial closed curve contained in this tori, in this torus here. For instance, this picture here with 2 homotopically non-trivial closed curves in the same torus cannot happen. This is the first claim. That is transverse almost for almost every t. It follows directly from Sard's theorem. So let us assume that there are two homotopically non-trivial closed curves, and the point is, since this end of sigma goes inside the cusp end forever, it can't go and come back and don't go inside again. So if you have two closed curves here, you should have a third one. And if you have this third one, at least two of them will bound a compact region, a compact annulus here. And now we use this foliation of this region by tori. And these tori, they come from horospheres in H3. So they have mean curvature constant 1 pointing upwards in H3, and that means pointing into the cusp end in our setting. So you just find the last contact point here between this compact part and this torus. This mean curvature is 1 pointing in, but this is strictly less than 1, so this is a contradiction, cannot happen. This shows that the curves are unique. So the picture is more like this. You could have more than one curve in the same intersection with a torus, but then one of the curves has to bound a disk, has to be trivial in the end E. Okay, now since that's the case, we are going to cut our end in some of these torus which we meet transversely and for a unique closed curve, homotopically non-trivial closed curve. And we will assume that the boundary is exactly this first curve here, and it's inside some torus which will reparameterize to T1. Now we want to prove that sigma has finite area. To do this, you just take the ambient distance function to this first torus here. We call this function R. And you find this inequality on the Laplacian, or the intrinsic Laplacian of the restriction of R to sigma. This inequality is quite easy to obtain. You find that this is less than h squared minus 1. And remember, since h is less than 1, this is a negative constant. Now you integrate over this compact annulus here, bounded by the boundary of the annulus and this homotopically non-trivial closed curve. So this is the picture we are taking. We take this compact annulus here, and we want to integrate this function in this region here, a compact region. So we obtain that this area estimate for the area of this region by an integral of the Laplacian of the distance function. The idea now is quite elementary. We just use divergence theorem to obtain that this area is controlled by the flux of this gradient field here over these two boundary components. However, what's going on here? We know that our surface goes inside the cusp end. So the gradient in this little part here, in this alpha t curve here, the gradient of the distance function and the conormal vector point in the same direction. Hence, this term here is positive, at least is non-negative. So we can eliminate this term on this estimate here. And we find that h squared minus 1 times the area is bigger or equal than this integral. Of course, this has to be a negative because this is negative, so this has to be negative. So the picture is correct here. So just make algebraic manipulation and you find that the area of this compact region is bounded by this number, whatever this number is. Flux times a constant here. This constant is negative, the flux is negative, so the area is bounded by a positive constant. And now we just make an exhaustion of the annulus by these curves, and you find that the area of the whole end is bounded by this constant, which depends only on the flux on the first curve here. So you obtain that the area of the whole end is finite. Since the surface has finite topology, it has a finite number of ends, and so it has finite area. Now, when you have a surface with finite area, it's elementary to... oh, I forgot to mention that Gauss equation implies that sigma has non-positive sectional curvature. So you have finite area, so your annulus, your ends should be closing. The asymptotic injectivity radius should be 0. And then you apply the first theorem. The asymptotic injectivity radius is 0, so they have total curvature equals to 2 pi times the Euler characteristic. And to obtain the claimed estimate on the total area, you just use Gauss equation. You know that you have finite total curvature. And you use Gauss equation. So you know that the sectional curvature is less than h squared minus 1. Remember, we are not still assuming that h is constant. By now, h is just a function which varies up to h. And so you get this, you just integrate this inequality here, and you obtain the area estimate in terms of the Euler characteristic of sigma. And what if equality holds? If equality holds, then lambda 1 should be equal to the mean curvature of sigma, and the mean curvature of sigma should be equal to h. So if equality holds, sigma is totally umbilic and has constant mean curvature. It's a remark that recently, Vanderson Lima, he gave a talk here Tuesday. He proved that actually, if equality holds, he proved a little more. In some sense, this immersion is rigid. The ambient space locally is locally isometric. If you have any immersion of a surface sigma with this equality in the area in a manifold with sectional curvature less than or equal to 1, then a neighborhood of this surface is locally isometric to a neighborhood of a surface in this hyperbolic manifold here. So it's kind of rigid. Okay, so we proved that sigma has finite area, and now we can begin to check what happens in the constant mean curvature case. Here is the setting by now. We have this half cylinder, which is an end of our sigma, and it Deu? Funcionou? Estão me vendo? Eu não vejo. Isso aqui não tem problema não. Alô, agora sim.
Oi.
The problem is if I don't want to drink water, right? No, so no water for me anymore. Okay. So this is the setting we have right now. We have half a cylinder going immersed into a cuspend of the ambient manifold. So now let's start bringing things to H3, which is a well-known space. Consider the fundamental, You consider the fundamental cover of this annular end by a horoball in H3. I'm calling it psi. And you consider the fundamental cover of the half cylinder by a half plane. So I'm calling it P. So this map here is trivial, and hence it lifts to this horoball. But this map, we know that is not trivial, hence it lifts to a half plane in H3. And this is the picture we are going to use. So we have this phi, this var phi, so we have an immersed surface upstairs, which is locally isometric to this surface downstairs. Let's make some assumptions which simplify the notation. We assume that the ambient end is isometric to this horoball, quotient by dx and dy. So It's not without laws of generality, but the ideas we use in the proof generalize. And moreover, if alpha 1 is generator of the fundamental group of E, we know that it lies inside a Z cross Z group, which is the fundamental group of C. It's a Z cross Z group. So we are going to assume that this element is 1, 0. It could be anything, but we are going to prove it in the case 1, 0 just to make things simpler. So this immersed half plane up there in H3 is invariant under exactly this parabolic translation. X, Y, Z mapped to X plus 1, Y, Z. That's why we are doing the simplification. Otherwise you would have X plus A, Y plus B, and you have a constant here, which is the multiplicity of the convergence. So this is the picture. We have this plane, this half plane here, which is, I don't know how to speak anything else. Periodic with respect to this tau translation. If it is periodic, it stays at a finite distance. It can be bounded by these two parallel lines here inside this horoball. And we are going to start understanding where this half plane lies in H3. So the first claim is that if the boundary is inside this minus C and C, you have these tilted planes here, and then the whole half plane lies inside this region. So let me draw you a picture here. We have here H3, but I am only taking Z bigger or equal to 1. And what do we know? That vertical planes here are actually totally geodesic. I'm calling these planes P0. And if you move these planes by a distance C here, I'm calling this other totally geodesic here as P sub C. Now you take equidistant surfaces to these planes. So it will be, I will draw the profile, it's better. So here is Z equals 0, Z equals 1. We have here our plane P0, not a plane, but I'm not a good drawer. And here you have two equidistant surfaces, PH plus and PH minus. These two, and you have also these other planes here, PHC plus, you have also PHC minus, and you have here PH minus minus C. So the first thing I am going to show is that since the boundary stays at this distance C from the y equals 0 line here, the whole surface must stay inside this region bounded by this plane, this horosphere, and this other plane. These are hyperspheres of constant mean curvature H. I forgot to mention that. So let's assume that's not the case. So you have some point here which is outside of a plane. How do you prove things now? You start with a totally geodesic sphere here, centered at the boundary at infinity of H3, which is below your height Z equal 1. So you know that this surface does not intersect phi of phi tilde because phi of phi tilde is immersed in Z bigger or equal to 1. Now you take an equidistant surface to it with mean curvature vector pointing upwards and with the same mean curvature of E tilde, and you start making these circles at infinity here converge to this horizontal line. So you take bigger and bigger circles, bigger radii, and make the center of the circles go to infinity as well, such that these circles here will converge to this line. And what happens? It happens something like this. The surfaces will converge to the half plane, and eventually, bam, you have your first contact point here. remember, all these surfaces here are at a bounded height, so they must, this is the picture, they can't be asymptotic to phi of sigma. You can't have this first contact point at infinity. So you have this and you contradict the maximum principle. So this is the case. It actually lies inside this region. We know that the picture is something like this right now, but we would like to see the asymptotic behavior of this surface here, so we would like to see that it is actually something like this. What did I do from this picture here to this picture here? I showed higher heights of H3. So how do we do this? How do we show things that are happening at infinity better? We bring them down. We just translate everything down. That's the idea. Consider a family of hyperbolic isometries of H3, which are exactly this. You bring this level to a lower level. You start bringing things to the origin of H3. What happens first? What happens to the planes P naught and PH plus? Well, they stay still. They don't move. They are invariant under this hyperbolic movement here. But the other planes, this parallel here, parallel in the Euclidean sense, they start moving towards the other planes. So every plane P something C goes to the P something E minus T C. So they start converging. This region R here starts moving like this until it converges to this region which we are calling R infinity. So what do we know? We know that the original surface lies inside this region, and when we apply these hyperbolic translations, these hyperbolic isometries, the region will stay inside every one of these surfaces, and the limit, if there is some, should be inside this R infinity region here. So we call E tilde infinity the limit set of the family, and it could be something very wild inside here. It could be disconnected. It could have in some places a lamination of a region here, of a foliation or something. And the next claim is not as wild. For each point in the limit set, you have a complete smooth H surface inside the limit set which contains P. So it can't be something like this. More like this is the picture of the limit set. How do you prove this? Well, actually, this is a proposition I'm not going to show, but the bound, the uniform, there is a uniform bound for the norm of the second fundamental form of E tilde. It's just a blow-up argument. You use points of almost maximal curvature and get a contradiction with the fact that you have finite total curvature. So since you have bounded the norm of the second fundamental form, it's quite easy. You pick a point at the limit set. There are graphs converging to a graph over the tangent plane, so you can just of uniform distance delta, and you just complete them all, and you get these leaves. So the next claim is that for every such leaf, actually it is invariant under a one-parameter group of parabolic translations. So it is like these planes here. These planes are invariant under all this group of isometries which brings x plus s, makes plus s for each number s. And the proof of this is the idea is very simple. These isometries here don't commute. What are those isometries? One is bring things down, the other is translations. So what's the idea? If you translate and then bring things down, is the same that first bring things down and then translate not so much. So this is the idea, and at the limit, since you are invariant under translation of 1, at the limit you are invariant under arbitrarily small translations, and you are actually invariant under a whole group of translations. A corollary of this is not very difficult to do, actually, since you have an ODE here, is that the limit set is actually contained into these two vertical planes. there is only one other surface inside this region which can be invariant under this group. The shape is like a teardrop here, so you have to prove that this local maximum to the height function cannot happen. This is a little work, but not too difficult. The last claim is to find the asymptotic behavior, actually. So the claim is that things are not wild like this at the beginning. They could be not graphical, but eventually after some height, everything that is above this height in this end is graphical. To prove this, assume not. So for every height, things are not graphical. And in particular, you have these tangent vectors dy in a sequence of points with height going up to infinity, where dy is tangent to them. And you again translate everything to the same point, and you find convergence. You find the limit point for this sequence, just a little work. If you have a limit point, then your limit set is non-empty, then it must contain a whole leaf. Then this leaf is either pH plus or pH minus, but neither of those have dy tangent, so you get a contradiction. And this contradiction proves that things are graphical after a while, so this is the picture. And the other result we just proved showed that the limit set is actually pH plus or pH minus. Now what happens, since it's graphical, the mean curvature vector points at the same direction after this height. If it points in this direction here, so it's asymptotic to this plane. If it points in the other direction, it has to be asymptotic to that plane. That proves the asymptotic behavior upstairs. But the thing is, when you use your fundamental map, your covering map, all of this go nicely downstairs to embedded annuli, which are totally umbilic. So that's the proof of the finite topology theorem. Now, how much time do I have? Now in the last 5 minutes, 6 minutes, I'm gonna talk a little about the existence theorem, how to find embeddings of constant mean curvature surfaces in hyperbolic manifolds of finite volume. Note that this result is not give a hyperbolic manifold and find a constant mean curvature surface. It's more like, I want something of constant mean curvature h, where can I find it? That's the result. We are given a number h less than 1 and finding a complete non-compact hyperbolic 3-manifold of finite volume with an embedded, properly embedded surface of finite topology and constant mean curvature h. The idea of this proof is something like this. You start with one totally geodesic example, any totally geodesic example. We know this exists by works of Colin-Adams. And you try to look to the parallel surfaces. Well, what happens in H3? This is a totally geodesic surface, and the parallel surfaces are of constant mean curvature h, and they are totally umbilic. So maybe if you have a totally geodesic surface here, which is embedded, we can make these parallel surfaces here go downstairs and be also properly embedded. The thing is, well, we know that these surfaces have constant mean curvature. This is the number of the constant mean curvature, and what's important is that it varies from 0 up to 1. When t goes to infinity, this function here goes to 1, but it never gets to 1. So the idea is, how far can I go embedded? So we fix some h, and we want to find a t naught such that such that sigma t naught is embedded and h of t naught is equal h. We begin with the ends of n and the ends of sigma. Oh yeah, I forgot to mention, this surface here has to have each end inside a different end of the ambient manifold. So you take an end of the ambient manifold, and blue will denote things in n, black will denote things in sigma. And what is the exponential, the normal map here? it goes to sigma t, which is something like this. It is this plane quotient by this z2 action, so it goes to something which crosses sigma but never crosses itself. So in the end, all sigma t are embedded. So we don't have to worry about the ends of n. We can look just in the thick part. In the thick part is compact. So what's the picture here? We have a part of sigma and a normal vector field, and we are going parallel distance t. How far can we go? We could start with a geodesic here, two geodesic going from two different points, and they perhaps meet. And this would be not good because then sigma t stops being embedded. So what the first thing is, if this is the setting, you can find the minimal length here. So you have a geodesic which is perpendicular to sigma here and here in geodesic arc. And since sigma is totally geodesic, you have a geodesic arc of the ambient space inside sigma, which joins these 2 points. And this curve have to bound ambient genus. They cannot bound a disk, because if they bound any disk, they bound a minimal disk, and you can't bound a minimal disk with 2 geodesic arcs in hyperbolic manifolds. So this is the picture. We know that if you don't have any topology, then you are embedded. Since you are compact, you can have a small neighborhood here of sigma, t sub n, such that for every t less than this t sub n, sigma t is embedded. The good thing about this t sub n is that it actually does not depend on sigma. It depends only on the injectivity radius function of the ambient space in the thick part. So it depends only on n. So the question to answer actually is this one. Given a t naught, any t naught bigger than 0, is there a hyperbolic manifold of finite volume n naught with this t sub n naught bigger than the given t naught, and which admits a totally geodesic surface sigma? So this is the approach to the problem, and the answer is yes. And the idea of proving this is first make a definite estimate on t sub n in terms of the injectivity radius. On the thick part, you start with any totally geodesic surface in n, as I told you before, and we assume that Tn is less than T naught, so if it was bigger or equal, we were good to go. If this happens, there exists a small geodesic arc with endpoints in sigma. Small, not actually small, but in some sense with control length. Then you go to finite covers of n. So since it's a finite cover, n hat will have finite volume, but you do this cover in such a way that sigma lifts isometrically to n hat. And this is possible because the fundamental group of every hyperbolic manifold is residually finite, and you also try to open the small geodesics so there is no small loops in your finite cover. Then you can go a little farther and you do it a finite number of times until you reach T naught. So that's it, thank you.